we are going to continue our example. As I mentioned before, the moment of inertia will be equal bh cubic over 12, and because this one it is not on the other at this distance, you multiply by the area times the distance square, plus this one. This one we assume the height of this bar, it is in the middle, it is negligible. Only we take the area times the distance square, and we obtain the 3 value here, and the total will be equal to 836 million millimeter square. Now sigma will be equal MC over I. We have two stresses now, one for the top part and one for the bottom part. Before, when we have symmetrical, we have the same distance. Now this will be equal to 137, and the other one will be equal 401 minus 137. Now sigma for the compression side, that means the top side, will be equal the moment equal to 120 kilonewton meter. We transfer it to in Newton millimeter times the distance 137.48 over the moment of inertia 836.78 times million, and we obtain in this one 120 times 137.48 divided at 836.78, and we obtain 19.71 megapascal. This is the stress on the compression zone. Now the stress on the tension zone, but also for the concrete, because we already transferred both of them on concrete, will be equal to 120 times million times 400 minus 137.48. That means will be equal to 262.58 152 equal divided by 836.78 million. We eliminate million up and million down, and we get time 120 time 262 152 divided by 836.78, and we obtain 37.65 megapascal. But this is stress at the bottom in the concrete. But if I need it in the steel, sigma tension now in the steel will be equal N times this sigma will be equal N times 37.65, and as we know N will be equal to 10. That means the stress in the steel will be equal to 376.5 megapascal. This is the way we can calculate the stress in the steel and in the concrete. Now, to make exactly the calculation, same way, if we have a slab, but the problem is the slabs, they have wider distance for B, and we can assume this B equal to, we take part of this slab, we take 1 meter, and we use it exactly the same way. That means if I have this slab and I have reinforcing some bar, and this is equal to, for example, to 4 meter, we take only 1 meter and we assume B equal to 1 meter, and we calculate how many bar we have in 1 meter, and this is the thickness of the slab. We take the distance from the steel to the top, and we use exactly the same way as the beam. But the only difference here, we take a wider section for the base of the beam. Here we have 250 millimeter, there we take 1 meter. In case of I have imperial unit, I take for 1 foot how much I have bar in 1 foot, and I assume my section, the width of my section equal to 1 foot, and in this case I can calculate how much the capacity of this in 1 meter or in 1 feet, depend of what unit I am using. It is exactly the same way if it is in slab or in the beam. And this is the difference between the composite section and the homogeneous section. In homogeneous section, all the material are same. Here, we transfer one of the material to the other one, and we assume it as homogeneous, and we do the calculation. At the end, we repeat it based on the ratio of the modulus of elasticity between the two materials. And this, by this explanation, we can finish the course of bending stress, how we can calculate it. And as I told you before, this is the maximum stress. If I need the stress at any distance, I can change the distance of C based on which distance I like to have these stresses. Thank you very much.